So hello everyone, we are the Group 10 reporters, and today we're going to tackle about the basic subsurface flow, steady state condition. The scope of this topic are the law of Darcy, confined and unconfined aquifers. So first, what is the law of Darcy? Darcy's law is one of the fundamental equations used in hydrogeology to describe the movement of water through an aquifer and shows that discharge is proportional to the hydraulic gradient and the aquifer material. Darcy's law states the principle which governs the movement of fluid in the given substance. Darcy's law equation describes the capability of the liquid to flow via any porous media like a rock. The law is based on the fact according to which the flow between 2 points is directly proportional to the pressure differences between the points, the distance, and the connectivity of flow within rocks between the points. Measuring the interconnectivity is known as the permeability. One application of Darcy's law is to flow water through an aquifer. Darcy's law with the conservation of mass equation is equivalent to the groundwater flow equation, being one of the basic relationships of hydrogeology. Darcy's law is also applied to describe oil, gas, and water flows through petroleum reservoirs. So, to understand the mathematical aspect behind liquid flow in the substance, Darcy's law can describe as the relationship among the instantaneous rate of discharge through porous medium and pressure drop at a distance. So Darcy's law is expressed as this equation. Q is equal to negative Ka dH over dL, where Q is the rate of the water flow, K is the hydraulic conductivity, A is the column cross-section area, and dH over dL indicates a hydraulic gradient. So let us going to apply the equation of law of Darcy. So here's a problem. A confined water has a source of recharge K for the aquifer is 50 meter per day and N is 0.2. The piezometric head in two wells 1000 meter apart is 55 meter and 50 meter respectively. From a common datum, compute the following: cross-sectional area, hydraulic gradient, rate of flow for K is 50 meter per day, and the Darcy velocity. So to compute the cross-sectional area, we need to multiply the average thickness of the aquifer, which is the 30 meter, and the 5 meter from the 55 meter minus 50 meters equal to 5 meter, and 1000 meter from the piezometric head in the two wells. So 30 meter multiplied by 5 and 1000 is equal to 115,000 meters squared. Then the hydraulic gradient, 55 meter minus 50 meter is equal to 5 meter divided by the 1000 meter is equal to 5x 10 raised to negative 3. So the rate of flow for K is the 50 meter per day. So to compute using the formula, so 50 meter per day multiplied by the 150,000 multiplied by 5 times 10 raised to negative 3. So we get the result of 37,500 meters squared per day. So to find the Darcy velocity, we need to use the formula V is equal to Q over A. So 37,500 meter squared per day divided by 150,000 meters squared. So we get the result of 0.25 meter per day.
Confined aquifers are a type of aquifer that plays a crucial role in a global groundwater system. And the definition of confined aquifers: a confined aquifer is a layer of permeable rock or soil that stores and transmits significant amounts of water, but is sandwiched between two layers impermeable, such as clay or rock. This confinement prevents water from flowing freely in or out of the aquifer, except through wells or other artificial openings. Aquifers, pressures. Confined aquifers are under pressure, which allows them to store water at a higher level than the surrounding water table. Second, impermeable boundaries. The aquifer is bounded by impermeable layers, preventing vertical flow of water. Third, artesian condition. Confined aquifers can exhibit artesian conditions where the water level in a well rises above the land surface due to the pressure. 4. Limited recharge. Confined aquifers typically have limited recharge areas, making them vulnerable to over extraction. First, leaky confined aquifer has a semi-permeable layer above or below, allowing some water exchange. Second, pressed confined aquifer has a highly impermeable layer above or below with little to no water exchange. And the importance of confined aquifers is: first, water supply. Confined aquifers provide a significant source of fresh water for drinking, irrigation, and industrial use. Second, agricultural support. Confined aquifers help sustain agriculture in areas with limited surface water resources. Second, third, ecosystems maintenance. Confined aquifers support ecosystems such as wetlands and streams by maintaining groundwater levels.
Good afternoon. I am Shane Natanya Pimenez, a member of Group 10, and for our report will be the basic subsurface flow, steady state condition, the law of Darcy, confined and unconfined aquifers, and my topic will be the unconfined aquifers. The pond next to me is fed from different several sources of water, including rain and snowmelts. But one of the main sources of water is the one that we cannot see. An unconfined aquifer is a body of water that is in sediment or rock just beneath the ground surface. Unconfined aquifers receive direct infiltration from the surface when it rains and snows. The surface of the saturated zone is water table, thus sometimes these are called water table aquifers. Since these aquifers are close to the surface, they are under little pressure, which means the water in this aquifer is able to rise and fall. Water table aquifers are usually closer to the Earth's surface than confined aquifers, and as such they are impacted by drought conditions and contaminants sooner. Because of these factors, having a drinking water well in an unconfined aquifer could cause more problems in the future compared to a confined aquifer well. Pumping water from a well constructed into an unconfined aquifer depresses the water table itself, called a drawdown or a cone of depression. Have you ever noticed when you're drinking something thick, such as shake or smoothie, the liquid starts to form depression around the straw? This is because the liquid is being drawn out of the glass faster than it can fill the space. The same principle applies to groundwater. A cone of depression occurs when a well is pumped at a faster rate than the water flowing in the aquifer. The water table then draws down into a cone shape, starting at the point where the well intakes water. This can happen anywhere. Pumping exceeds the rate of flow, excluding the agricultural and residential landscapes. Since this draws down the water in the soil, pumping needs to be managed because not only it will affect the well, but it can also affect the other wells close by that may not be as deep in the soil. These wells will either lose water pressure or receive no water at all. Once this depression occurs, they usually are not permanent. And once the pumping slows or stops, the water table quickly go back to normal. When we think of a cone depression, we usually see this happening in unconfined aquifers, but we can also have drawdown in confined aquifers, where we should see just a lowering of a hydraulic head versus a cone shape of the water. Even though this depression can often fix itself fairly, quickly pumping should always be careful. Manage to avoid overpumping. Significant drawdown over time cannot be repaired.